So there's a bit of a situation here. I am chairing for myself. So Mia hasn't showed up. She was going to do this, but I will introduce myself instead. So the next talk is for Brett Lewis. Please give him a round of applause. Okay, so let's keep that energy up. It's the last talk of the day. I promise I won't take too long and bore you all as much as, well, actually I don't promise. My name is Brett Lewis. I'm from Queensland University of Technology, and I'd like to welcome you here to this talk. I'm going to speak about novel bioadhesives for rubble stabilisation. Rubble stabilisation. So what is a rubble reef? Well, it's definitely not that. This is a rubble reef. Why is it a concern? Well, what happens is when we get an increase in rubble, we often get a decrease in three-dimensional complexity of these reefs. That means the reef becomes a little bit flatter, a little less complex. What happens then is we get a water diffusion, or less water diffusion, a decrease in water diffusion. This ultimately will increase water velocities. When water velocities increase, we often keep this rubble in motion, and that's when the rubble becomes a bit of a problem, is when it is mobile. Once it's mobile, there's less available substrate for natural recruitment, but there's also less available substrate for us in restoration. So these rubble patches become a bit of a concern, particularly globally, as RAP tries to scale up. Our mission now is to save Earth's reefs. We need to take into consideration rubble patches because they are a huge problem throughout the Caribbean and are a growing problem throughout Indonesia and other Pacific islands. So how do we stabilise rubble? Well, we're going to have a bit of a look at how it naturally stabilises first. There is a two-step process. Which the first one is preliminary stabilisation. So this was from a publication by Cesarelli in 2020. This preliminary stabilisation is the initial steps. This requires interlocking of the rubble branches. It then requires pioneer binders, which are algae coming over the top. And then there will be intermediate binders, so sponges, ascidians, softer binders that will come in and form a matrix around this rubble. And start that stabilisation process. So then CCAs, calcium, carbonate building biomineralizers, microbialites, I should say, and corals can come in and start cementing that framework together. But of course, as you could imagine, as those hydrodynamics increase, as three-dimensional complexity decreases, and these cycles of constant destruction of reefs continue, these processes are going to stop happening. However, the good thing is they give us a bit of a roadmap as to how we could stabilise reefs and do it pretty effectively. So recent research into these areas by Tanya Kenyon and her team have started to have a look at how strongly this rubble is required, like what kind of binds are required in and around this rubble area. And they found that the forces that these binds usually consist of are around 12 newtons. So this gives us a bit of a framework, what forces we need to achieve with a bioadhesive in order to potentially, create a framework ourselves. At the same time, what are the velocities that these are resisting? So ambient velocities that these resist are about 0.2 to 0.8 metres per second. So again, we're starting to produce a framework for how the bioadhesive might work. But before I move on to any results, I just will talk to you about the bioadhesive because I'm sure not everyone is an adhesive expert. So number one, cohesion. Number two, adhesion. They're the two things you need to know the most. Whenever it comes to, even if you're going down to Bunnings, they're the two things you need to know. Cement has great cohesion, which means it's hard. It holds together. It holds its structure. Gum has terrible cohesion. It gets pulled apart very easily. right? But gum has great stick. It'll get in your hair and you'll never get it out. Cement, it takes a little while. You'll be able to wash that out as long as it's wet still. So it has bad adhesion. Now, these are two factors that we look at. However, there are other things like durability, which is the other two factors over time, and it's this tunability. Now, this is the reason in the first place that RAP started looking at bioadhesives, is because of this tunability. What that means is we can take any chemical component and start adding it to the bioadhesive to basically change how it behaves, right? And this allows us to create a bioadhesive that is fit for purpose. Of course, just developing a bioadhesive takes quite a bit of time, and then testing it also takes quite a bit of time. So we can start to add things like starch, cellulose, other plant wastes into this material, cheap products, and we can start changing those factors. But since I've come on board, we wanted to expand that a little bit more. We want to create a suite of adhesives for rubble stabilisation. That means looking at other different things like magnetism, the viscosity of the material, the biodegradability, and of course getting that cost as cheap as possible. And just to give you an idea what cheap means in the bioadhesive world, QT just sold a bioadhesive for $80,000 per 100 grams. That's what it gets sold at the moment at market value. Ours should be around the $2.50 below mark for 100 grams at the moment, but we should be able to get that lower as we continue to talk to companies. So other things you need to know is that it's plant-based, it's 75% biodegradable, 25% degradable. It uses a cross-linking attachment mechanism rather than mechanical, which most adhesives use. Cross-linking is a chemical process, so it chemically bonds to the surface. And it's made from common plant waste material available globally, anywhere. So it makes it easy for us, not just here on the Great Barrier Reef where we have a lot of resources, but also in other countries where they may have less resources, but as long as they've got palm oil or cane farms, they're going to be able to build this bioadhesive. So for the last 12 months, I've come on board to basically take this base bioadhesive that was built over the first 3 to 4 years of RAP and test it and refine it and test it and refine it and produce this suite of bioadhesives for a rubble stabilisation here, but hopefully broader applications as well. But I will only talk about rubble stabilisation. So the first thing we want to look at is compatibility. Is it going to be okay for the reef? And you can see here the blue line at the top is the red line at the top. You can see here is what happens when you put the bioadhesive in 200 mils of water. You get a deoxygenation event. Obviously, corals and a lot of marine organisms don't like this, right? So we wanted to see whether or not that's going to scale. So even just putting it in 500 mils of water and running the same trials again, we saw the deoxygenation event shifted more towards the control. And basically, as we scale to ocean levels, I really don't see that being a huge problem. And we did find that whenever we place anything next to the bioadhesive, they all survived. But of course, we want to continue to test these things. So we had a look at some clean substrate tiles and placed the bioadhesive on that to see what colonized around it in the aquariums at the Sea Simulator. And we can see here that there actually was a bit of a shift. So compared to the controls, we had an increase in CCA and a decrease in fleshy corals like lobos. So there was a bit of a shift, and it was significant as well. However, that didn't show on the actual rubble pieces. So when we tested this bioadhesive on the rubble, we saw no population shift at all. That's likely because there was already a fairly well-established community, and it was probably difficult for the bioadhesive to get involved in that. But at least it didn't shift the community, and we did actually have some spats start growing in and around the bioadhesive on those rubble pieces. That brings us to the bad result. So when we tried to settle algae around it, and you could imagine what it would be like to do this in 10 mil of water, there was a heavy deoxygenation event, and it killed the spats in 10 mil of water. I'm sure at scale it's probably not going to be a big problem, and you can see with the spats in the previous image, it doesn't seem to be. However, we did take this result and we wanted to have a bit of a look, and we started tuning a new adhesive using an alginate. And it settled 50% of spats once we were done with that. And all larvae were alive, all planula were alive at the end of the trial. So that was over 24 hours. Both trials were. So compatibility-wise, it looks pretty good, especially for rubble stabilisation. We also want to have a look at the strength. So we did 2 tests, one on rubble and one is a standardised process. So at the bottom there you can see that's the standard, so it's just a little plug-on-plug action. It's just giving us a flat surface, something that we can replicate. And then the top one is obviously rubble. It's going to be a lot more inconsistent, it's rounded, irregular texture, and so on. And plus it also has a biofilm, which is painful to try and deal with. But what we found was the T2 on the right, so to give you a bit of context, the T2 is the first bioadhesive that we produced, and the T2 is the bioadhesive I was given at the beginning of this project. And these are the new ones that we've developed since then, the R1 and AG5, and they're producing much better forces. And when we compare that to what the forces of binding are in a natural reef at that early preliminary stage, at 8 to 12 newtons, these are significantly going beyond that. And just to give you an idea, kPa is just newtons adjusted for surface area, so it's a relative number. It's actually a conservative number. The newtons are actually significantly higher than this, so that pulls those numbers down. So we're absolutely outstripping natural binding. And you can see it there. Again, that's on the rubble pieces themselves, so not on the standards, that's the rubble and the difference between them. So then, of course, we want to go to translation, we want to start scaling up, we want to start testing things. Next, we wanted to look at, oh, the video's not playing, okay. But that top one there is a flume system. Oh yeah, there you go. The top one there is a flume wave system where we tested the bioadhesive in that, and over all 24 sets of experiments that we did, we never had one piece of rubble move or detach during that at 0.5 meters per second. Now, it's only at 0.5 meters per second. They're ambient conditions on the reef. Obviously, you're going to get worse. But just to be clear, we're also never going to stick down one piece of rubble at a time. That's never going to be the goal. It's going to be creating a mass. So we really want to see how the mass will interact eventually. But we also wanted to test this at higher flow rates. So we got them to resist at 20 mils, only 20 mils of adhesive, a very small amount of adhesive was able to resist 1.4 meters per second. So that's about 3 knots. So that's pretty good. But of course, we'll hopefully continue to refine and make that even better. Other things that we're looking at now is we're testing different methods for outplanting. Austin, even though he's not in the room, had a great idea of this nucleic kind of centralizing coral reef restoration, similar to what they do with deforestation or reforestation. And we want to do a similar thing, create nucleuses of stabilized patches and then hands-off allow the natural processes to then take over. So long as there is a stable area for the rubble to bind and interlock to, it should do it itself. And the good thing is, if it fails, if we fail, if this doesn't work and we do put a bunch of this stuff out on the reef, in 5 years it won't be there, which is not what we can say about a lot of our interventions. Obviously, it would be the goal to be like that, but this one, hopefully, we won't leave any footprint behind regardless, other than a good footprint, hopefully. But thank you for listening to my talk. Oh yeah, and hopefully in 2025 we'll scale up to those that reef scale application. I have to keep my own time, so I need to move myself along. So thank you. I'd like to thank everyone that's on this screen and everyone in this room for sticking through the conference and coming to my talk at the end of the day. I think that's lovely, and you're all my favourite people. Thank you. Do you have any questions for me? I just realised I'm still chair. Thanks, Kevin.
No, thank you, microphone guy. Thank you, microphone. There we go. Thank you, Brett. Yeah. Brett, I'm going to need thousands, tens of thousands of kilograms of this bioadhesive. I'm scaling everyone. I need that. How can I have that much, and who's going to make it for you? And is that available in this state or in this continent?
So you'll have to speak to Adrian Baker. He is my only person that I have making the adhesive at the moment, and he's not even full-time. So at the moment we're in we're trying to start discussions with Henkel and Sika, both two of the world's largest adhesive producers and manufacturers. And there are some potential other avenues, but we really do need a lot of this stuff. And I don't know yet how that's going to look. Hopefully they can also make it cheaper because they'll have supply lines that we don't. Thanks, Kevin.
Brett.
Anybody else? That's the last talk.
Thank you. I'm just wondering what the basic setup times is for this glue.
So for like rubble application or just to make it in?
Yeah, for gluing applications.
So for gluing applications, to make the bioadhesive, it's actually really quick. It takes as long as you have the materials there. I've seen them, and it's only small amounts that they're making for me, but they can make it in like 2 or 3 minutes. It's all mixed together. Obviously, when you're scaling, and it'll probably take a little bit longer, so I wouldn't use that as an accurate timeline. But to apply it underwater and to deploy it, and that's something that I'd really have to work out logistically. I really don't have an answer for it. I hope that everything will work perfectly and we'll be able to deploy this rapidly. But for now, we'll just have to get some divers down there with some buckets and see how it goes.
But what's the actual, like once you apply it, what's the setting times on it?
Oh, setting time. Oh, okay. So sorry, with the bioadhesive, it doesn't have a setting time.
Oh, right.
Cements and things like that, they often have a curing time. The bioadhesive won't cure. It will adapt to its environment. So I actually meant to bring a sample. It's in my bag. Is it in that bag? Yeah. And so it'll be hard, right? To start off with, in the air, you can have it hard, but if you place it underwater, it will soften again. Or if you place it underwater, it'll start to harden to a certain degree, but it'll never get completely hard. And that threshold as to where it reaches its maximum, we're still kind of working on, but we see after 15 days, it's still getting stronger.
Yeah, okay.
So we haven't quite hit that mark. I'm testing over 30 and 60 days now. So the first set of trials were just for 15 days over 10 adhesives, and now we're testing, refine those adhesives, picked a couple, and now we're going to test it for longer to see if it continues to get stronger over time.
Okay, thanks.
Thank you, Brett. Everyone can head off to the plenary, straight to the plenary, everyone.